Well, I found a couple problems that have to do with atmospheric chemistry, which almost always involves radicals. 923 looks at ozone decomposing into oxygen. It's actually one step in a larger cycle of how ozone protects those of us at the surface of the Earth from ultraviolet light. But this piece just looks at one little reaction and a proposed mechanism. And it asks us to do a little bit with this. The first asks us to look at the rate law based on these mechanistic steps. The idea that a pre-equilibrium occurs is something we've seen before, and that a slow step really determines the rate of the reaction. So if I write the rate law based on the slow step, I'm going to write, whoops, I forgot to write this in the preamble there, but I'm going to write the rate constant of the second step times the concentration of oxygen atoms times the concentration of the ozone. The oxygen is in the category of an intermediate, so we're going to use a expression derived from the first step to substitute for that. The practical reason is that intermediates are often really very low in concentration, and so they're really difficult to measure in the lab. And so if we take the first reaction and essentially using the definition of the pre-equilibrium, that is the rate of the first step is going to be equivalent to the rate of the reverse. And please forgive me here, all of these K's that are rate constants should be lowercase. We have this equality, and if I rearrange it to solve for the intermediate, my handwriting is deteriorating as the day goes on. We have oxygen atom right there, and when I substitute, when I substitute that back into the overall rate equation, I get kind of a mess of, the technical term, a mess of rate constants times, I'm going to have ozone really to the second power in the numerator, and then I have oxygen downstairs here. And I could re-express this as an observed rate constant times ozone squared over oxygen to the first, which mimics what we were given in the original part of the problem. I think they asked us one other question. Why would the rate of this reaction decrease if the concentration of oxygen increase? Mathematically, that makes sense, because if you see here, if you have a component that's in the denominator increase, that's going to make the rate of the reaction decrease just using the math. But in sort of a descriptive way, we want to look at the pre-equilibrium. And via Le Chatelier, if you increase one of your products, well, that's going to have the equilibrium respond by shifting to the left, which is going to slow down the reaction. So let's take a look at the second reaction, which is also an atmospheric chemistry example. I think I mentioned to you in class that they use a lot of gas phase reactions when teaching students kinetics, because you don't have really solvent getting in the way, and reactions are a little cleaner. Here we have what happens when CFCs get thrown into the mix. This CFC is dissociated when it gets hit by some ultraviolet light to create a chlorine radical. You can see that this sort of populates the stratosphere with some chlorines, although it's not part of this reaction, we're told. Basically, they want us to figure out the overall reaction of these two steps here. So let me go to a more sensible color there. And all you do is add it up like a arithmetic problem. Everything on the left is going to get grouped together. I have this habit of throwing in dots just to tell me that I've got a radical present. It's not really essential. And on the right-hand side, I've got all of these species. I have oxygen, I have a chlorine radical and another oxygen, and I think I've got a little bit of canceling here. There's a chlorine on each side, and I've got this species on each side. So I have an oxygen atom, an ozone, going over to two oxygens. That's the overall reaction. We're asked to identify the species that were in our mechanism but don't appear. You could see that because the ClO radical is created in the first step and consumed in the second step, by definition that's an intermediate. Catalysts, on the other hand, are species that get thrown in on the reactant side but then emerge unchanged. So the chlorine here is a catalyst. Let's see, another question. Why is the fluorine radical not important in this mechanism? A fluorine radical would involve the CFC getting hit by ultraviolet light and producing this species. That's probably going to happen at a much lower percentage, just simply because carbon-fluorine bonds are much stronger. One of the reasons that CFCs do the damage they do is because there really isn't much at the surface level of the Earth to break those bonds into some byproduct. So they can survive many, many years, if not decades, and just migrate up into the stratosphere. We're also asked to, it says, one suggestion for reducing the concentration of chlorine radicals is to add hydrocarbons such as ethane to the stratosphere. How would this approach work? If we take a look at ethane, the assumption there is that maybe you could do a substitution reaction, kind of a classic organic chemistry reaction, where you can do some very easy one-to-one stoichiometry and not have any radicals present in your product. So that makes a lot of sense. And then finally, we're asked to draw potential energy versus reaction progress diagram for uncatalyzed and catalyzed by chlorine radicals for the destruction of ozone. So on the previous slide, we had just a very simple reaction of oxygen atoms and ozone resulting in two oxygens as products. And you can imagine that you're going to need a fairly serious collision between those two to break the bond at exactly the right place. For a reason we talked about in class, I recall, that oxygen is going to have to really hit that bent ozone in a proper place to get this product. On the other hand, when radicals are involved, you can get some things happening that don't have such a barrier. And so what we have here is the assumption that there's a smaller activation energy. Maybe you could make an intermediate that is going to react with, can't read my writing here again, and end up with my radical unchanged and then my two oxygen molecules over here. So just at the simple level of not having to have molecules orient themselves so perfectly is going to lower your activation energy and basically lead to a more efficient formation of the product. In the end, whoops.